This video is all about the two wave types, comparing and contrasting them and identifying examples. These two types that we will look at are transverse and longitudinal. We're going to identify their elements, the elements of waves, the most important characteristics of them, through looking at simulations, images, diagrams, and then we're also going to start looking at some equations that talk about the relationships between these elements. So we start out in your notes with the definition of a wave, that it's just a transfer of energy that travels through something, a medium. Now, it could be that it travels through nothing. The medium could be nothing, like in space, or it could be that it's traveling through air, or earthquake waves travel through the medium of the ground and soil, or it could be through train, like the metal parts of a train track. All sorts of different mediums that waves can travel through. Longitudinal waves, everything is in the same direction. So I would write something down. Remember, during these videos, follow along with me on your notes. So think of it as everything kind of is in that long way. And so sound is a great example. If you look through a slinky, this is where you kind of pulse or push through the slinky. And everything is going to be going in that same direction. So you can see the disturbance is traveling to the right, and the energy within the disturbance is to the right as well. Now, transverse waves, obviously now we have two different directions. And it looks like this video doesn't want to work. But you can imagine what we're seeing here, that the disturbance is going, oh, there we go, is going to kind of go up and down. Now, it doesn't have to always be up and down or left and right or whatever, but it's the important thing is that they're different. Where can we get back? Transverse, we have this perpendicular or different directions happening. Trans does mean different. Waves on a string, water waves, and electromagnetic waves, which doesn't mean much to you now, but our next unit is going to be on light. And this is the light that we see from a light bulb or the sun, but also there's lots of different types of light waves, like X-rays and gamma waves and radio waves. So those are the two types. Now, if we look at elements of waves, we can look and draw these on the two different types, and they are really similar. So here in this large picture, we have transverse, which is what we're used to seeing as a wave. But we can also view waves as longitudinal, thinking that everything is going in that same direction. So nothing is moving up and down. Whereas our transverse wave has this up and down disturbance and this perpendicular traveling. You have the definitions of these different aspects on the next page. So take a second to pause the video and read through these definitions. I'm going to keep going and just talk about the main ones on our picture here. So really the most important is wavelength of a wave. And you'll see it as this lambda. I usually write it like that shape. This is something we'll calculate, draw, and talk about a lot because it determines a lot of important and interesting things. It's a distance, and it's the distance between two of the same points on a wave. So if we look, what's the same point? Well, this high point is called a crest. So crest to crest, that's a wavelength. We could also say trough. Now this is tricky because This is a trough too, but think about this trough as going down and this trough is going up. Those are not the same points. Oh, sorry, these aren't troughs. These are equilibrium center points. A trough is just a low point over here. Anyway, so we have this equilibrium point, this one. Now these two are the same. So the wavelength would be that. You can notice this distance, the wavelength doesn't change in a wave. But we could also choose some just random point. This random point going up, not this one, but this random point going up. So that would be the wavelength. Now we can do the same on longitudinal. Instead of crests and troughs though, we just have compression zones where we have many different molecules moving together, and we have expansion zones. Expansion zones are sort of like a trough or a lack of, and compression zones are sort of like a crest or a high point. If you think about compression and expansion as pressure amounts, compression is where the most pressure is, aligning to a crest or peak, and expansion is where the least is. So if we're drawing a wavelength, we could say from compression to compression, that would be a wavelength. From expansion to expansion, that would be a wavelength. From midpoint compression to expansion to midpoint compression to expansion could be a wavelength. Wavelengths are always in that long direction. Now the one other important aspect or element we're looking at here is only in a transverse. We won't really look at this in amplitude, but or in longitudinal. It gets a little tricky, but it's about the height. And so it's the height from the equilibrium or midpoint to equilibrium or midpoint to a crest. Oops. And vice versa. To a crest, equilibrium or midpoint to a trough. Okay, notice it's not that. That is not what the amplitude is. That would be twice the amplitude. The amplitude always starts at that equilibrium line. Again, you have everything defined for you here. There are two things here that we did not talk about. These relate to speed but are different. And we're going to look at them with equations next, but there's all of the definitions of what we just talked about. So period and frequency are inverses of each other. They have letters that we use in formulas, and if we have one, we can always know the other because they're these inverse opposite things. So period is about time. It's the time it takes for one oscillation, for a wave, but also a pendulum, a spring, anything. So an oscillation would count as the time here to go back to that original position. Or it could be the time for, if we have this wave that's moving along, the time for a wavelength to pass. So one oscillation is a fancy way of also talking about a wavelength. Period, you might think would be P, but that's momentum. So period is capital T because it's related to time, but it's not lowercase because it's not just any time. It's measured in seconds. So if you have an increased period, like 100 seconds or something, that's a very slow wave. Most likely, depending on what the wavelength is. A decreased period is in general going to be a faster wave, but again, it depends on the wavelength or the distance that it's traveling to is kind of a way to think about that. So frequency is the opposite, whereas period was seconds for one oscillation. If we switch those, that gives us frequency. Number of oscillations for every 1 second. And remember, an oscillation is like saying a wavelength. Frequency is measured in hertz. And this is my favorite pun, but we can say the frequency of physics jokes, hertz. Hertz you'll see with a capital H and a lowercase z. So 5 hertz is a frequency. Frequency is lowercase f, the same thing as friction. And we have a very simple but weird looking equation to relate frequency and period. We can write it like this, saying frequency is 1 divided by period. Or we can say period is 1 divided by frequency. These are the same thing because they are just inverses, which is a fancy way of saying mathematical opposites of each other. Now, the last equation that we're going to look at is relating this frequency idea to wavelength and finally to velocity of a wave. This is the number 1 equation of the unit. So it should get some extra attention, some squiggles, some exclamations, some marks. So it just says that velocity equals the frequency times the wavelength. Velocity, remember, is in meters per second, our old friend. Frequency is in hertz. Frequency of physics jokes hertz. Wavelength is in meters. Now you can use this equation in combination with the period equation, period and frequency, and depending on what a problem gives you. So let's just look at a couple quick problems in the problem set. Number 1 and 2 in your problem set are only looking at period. Remember big T and frequency little f. So it says on the beach, you notice that 14 waves crash into the sand in 60 seconds. What is the period? We can think about this 2 ways, but remember period is seconds for 1 oscillation. Oscillation is like saying waves or wavelength. That's all kind of describing the same idea. So if I put the seconds and divide it by the oscillations or the waves, that gives me the period. Just keep this color, so 60 seconds divided by 14 oscillations. Type it into your calculator, that gives you the period. Now to figure out frequency, we could do this 2 ways. We know that frequency is oscillations divided by seconds. Remember, oscillations is waves or wavelengths. So we could say 14 divided by 60. That would give us the frequency. We could also say the frequency equals 1 divided by the period that we got up here. And that will give us the same answer that this gives us. Either way works, and either way is following the formula and the relationships. Make sure you go to this wave simulation sometime if you don't get a chance to in class or while you're watching this. It's really helpful to see these things as the waves move. If we look at wave calculations, we'll just do number 1 and 2 here together, and 3 has the key answers for you to work on your own. Number 1, if a wave has a frequency of 5 hertz, frequency equals 5, and a wavelength equals of 2 meters, how fast is it moving? That's asking for a velocity. Well, our velocity equation says that frequency and wavelength multiplied equals the velocity. So I take my 5, that's my frequency. I take my 2, that's my wavelength. And I get 10 meters per second. Now that is how fast it is moving. While frequency feels like it's speed, it's not. It's about the number of up and downies, the number of waves, the number of oscillations. Number 2, if an ocean wave passes by once every 2 seconds, here we have time, period. And the crests are 10 meters apart. That's defining wavelength. How fast are the waves moving? Velocity. Many times we use equations in combination here. And here's an example. So in order for us to use the number 1 equation of the unit, we have to have frequency, which we don't. However, we have something that directly relates to frequency. And period is just 1 divided by frequency, or frequency is 1 divided by period. So frequency is 1/2 if the period is 2. We could also say it's 0.5. Now that I know the frequency and the wavelength, I just multiply them. And we get 5 meters per second. You have several class problems that involve these two formulas, so go ahead and take a look at those and do some practice.